it's a pleasure to speak in a conference in honor to Evgeny and the 10 years of Algebra at Lincoln. Particularly very glad I am part of this 10 years of Algebra at Lincoln. So I joined Lincoln around 2.5 years ago, and it has just been a pleasure to work there. So it's a pleasure to be part of its history. And I don't know, it has been absolutely great to work there. I really enjoyed the atmosphere of our School of Maths and Physics. So the colleagues are great. We have nice students. So everything has been amazing. And in particular, it's very nice to be there because of Evgeny. Evgeny is one of the nice colleagues that makes this atmosphere so great. And well, I don't need to tell you that. I know that in this conference we have lots of collaborators of him, people that have worked with him mathematically or otherwise. So I just would like to start the talk by saying that I'm thankful for all the work together and for all the conversations we had, both mathematically and so mathematical conversations and otherwise, and all the advice and support, especially at the beginning when I was starting at Lincoln. So it has been great. So it's really an honor to be giving a talk here today. And I will be talking about twisted conjugacy. Twisted conjugacy is an area that has been a research topic that has been growing the past few decades. I'll start by telling you what twisted conjugacy is. I'll give you some examples. I hope I can motivate it well enough so that you also feel excited about this area as I am. And then I'll just talk about a result that I have in a joint work with Yuri. So let's start with twisted conjugacy. What is twisted conjugacy? Well, as the name suggests, this is a generalization of usual conjugacy. So we start with the group G, but we'll have an action that resembles the usual conjugacy, but it has a twist by an automorphism or an endomorphism. More generally, you could define this for endomorphisms too. So we take a group G, an automorphism or an endomorphism phi, and then we define an action that is, well, an element G acts on an element X by Gx phi of G to the minus 1. So clearly, if I take phi to be minus identity, we recover the usual conjugacy. So in this sense, this is the generalization. And also, when we have conjugacy class, usual conjugacy, we call the orbits of the action conjugacy classes. Here we'll be calling this the phi twisted conjugacy classes of this automorphism. So obviously, if I take here the identity twisted conjugacy classes, this is just the usual conjugacy classes. I'll explain to you, give you a motivation for you. One of the reasons why researchers are interested in this area is because of its connections with algebraic topology. And then in that context, people usually call this Haidameister classes because it's related to some homotopic invariant called Haidameister number. But here I'll be calling this twisted conjugacy classes. If I say Haidameister class, it was probably a mistake. Okay. So because of these connections with algebraic topology, we are interested actually in the number of such classes. So we want to know what is the number of phi twisted conjugacy classes for a fixed automorphism. So this is something that was named. So this is called the Hadameister number of an automorphism or an endomorphism. If you take any endomorphism, just define the Hadameister number as the total amount of phi twisted conjugacy classes. And then we define the Hadameister spectrum as all possible Hadameister numbers when you take all automorphisms. So here we really define this just for automorphisms. Okay, so just to give you one example, so the standard example is Z. So Z has only two automorphisms, identity and minus identity. We already know that because this is infinite abelian, it has infinitely many conjugacy classes. So the Hadameister number of the identity is infinite. So if you look at the the twisted conjugacy classes of the minus identity, so I take an integer number A, this is by definition the set of all elements of the form. So some integer number z plus a minus, then minus identity applied to z, which is just a plus 2z. And then we range over all integers. So it's clear that if a is even, we get that this class is composed of all even numbers. If a is odd, then we get all odd numbers. Therefore, we have precisely 2 classes for minus identity, which we can just write in symbols as the Hadameister number of minus identity is 2. And then using the spectrum notation, we conclude that the Hadameister spectrum of Z is just 2 and infinity. Those are the 2 only possible Hadameister numbers for Z. Okay, so I'll give you one slightly more interesting example, but it's still, well, Z2. So for Z2, notice that for each positive integer, we can define an automorphism group phi n, which is given by this rule. We just send the pair xy to these linear combinations of x and y. And then this gives an automorphism. And if you take here an element ut, a pair ut of Z2, and you want to know what are the elements that are phi n twisted conjugated to them, you need some x, y, and Z2, then you know that by definition, being twisted conjugated to ut is just xy plus ut, then minus phi n applied to xy. And then you get this rule here for this. So if I want to know what the full Hadameister twisted conjugacy class is, we notice that, okay, if I take any pair in Z2, and I want to know if this is in this class, we first notice that I can take the second entry here to be any integer number that I want. So I can always take any element. We know that every element in Z2, in Z, let's say, would be in the second component of the elements of the twisted conjugacy class of ut. So we could think that x is fixed so that I can see what's the freedom I have to find elements in here. And then we see that I would have that the only elements I can reach here would be the ones that are u plus an x minus n y. So I can only move y here. So all elements I'll reach here, they are congruent to u plus an x or u mod n. So we see that we have precisely n twisted conjugacy classes. So first one would be all integers that are congruent to 0 mod z, direct product z, and so on. Okay? So here we see that we have all possible positive integers as Hadameister numbers for Z2, but we also know that Z2 is infinite abelian. It has infinitely many conjugacy classes, and therefore the Hadameister number of the identity is infinite. So we get that Z2 has this special Hadameister spectrum that has all possible values for automorphisms. In this case, we just say that Z2 has full Hadameister spectrum. Okay? In general, we can show this for any Zn. Okay, so maybe one more example. It's still in the abelian case, but I'll speak about different cases as well. So for each prime p, just recall that z and then 1 over p means I'm taking the group of all rational numbers whose denominator is a power of p. In other words, it's just a group z where I allow also division by powers of p. Then the Kippe and Gonçalves, they show that if you take any infinite set of prime numbers, then the group given by the direct sum of all z1p's, where p is one of those infinitely many primes, this has Hadameister spectrum composed of only the identity. In other words, if I take any automorphism of this group, it always has infinitely many twisted conjugacy classes. And this is a special property, especially because of the connections with algebraic topology. I'll talk about this in a second. So we name it. So this is called property R infinity. We say that a group has property R infinity if all twisted conjugacy classes have there are always infinitely many twisted conjugacy classes for all automorphisms. Okay, so some examples of groups that have and some groups that don't have R infinity, or I'll start with this one. If you take Z semi-direct product with Z1, 2, or cyclic group of order 2, you get where the action is non-trivial, then this group has R infinity. And you might be asking why this very specific group is my first example. And the reason is I wanted to illustrate that R infinity is not inherited by subgroups. It's not even inherited by finite index subgroups, despite what one might think at first, because we've already shown that Z does not have R infinity. Some more interesting families of groups that have R infinity are, for instance, the free group Fn of rank at least 2 by Levitt and Lustig. So De Quimpe and Gonçalves, they show that if you take free nilpotent groups of nilpotency class C and rank R at least 1, so you can think of them as just a quotient of the free group with the C plus 1 term of the lower central series of Fr. So this will give you a nilpotent group of nilpotency class C. Then these groups, they have R infinity property as long as the nilpotency class is at least twice as much the rank. So here we get an example of a family of groups where you have members having R infinity and members that don't have R infinity. And then just to give you a different flavor, there is this work by Altair, Yuri, and I, where we show that certain Thompson's-like group have R infinity. Okay, so I promised you a motivation in topology. So motivation is on fixed points. So suppose you have some homeomorphism of a topological space, and you want to know if this homeomorphism has fixed points. You want to get information about the fixed points of these homeomorphisms. So here, usually we need to consider compact connected topological spaces, but I just want to paint the picture, so I won't give much detail. So bear with me. When you have this homeomorphism, you can take the lift to the universal Culver, and this lift somehow will induce a group automorphism on the fundamental group of this topological space. Now, if you're unfamiliar with all of these terms, all you should get from this slide is that if you start with a homeomorphism of certain topological spaces, you get a group automorphism. And we know that group automorphisms, they have Hadamard numbers, right? And the fun part is that in fortunate cases, this Hadamard number will actually give you information on the number of fixed points of F. So here I have one result to illustrate what I mean by giving information about the fixed points. This is not really a theorem by someone, but a concatenation of results, but it says the following. If you have M, a certain kind of compact manifold, then this induced automorphism having infinitely many twisted conjugacy classes is equivalent to this homeomorphism being fixed point free. Now, it's important to mention that this fixed F is actually up to homotopy, so we are taking fixed points that you cannot get rid of them by deforming your homeomorphism continuously. So here we mean like fixed points, but up to homotopy. But then the idea is, if you know that the fundamental group of this manifold has R infinity property, then you know that no homeomorphism of this topological group has a fixed point, at least up to homotopy. So that's where the interest comes from this sort of work. And I also would like to stress out that even when the Hadamard number is finite, in fortunate cases, we have that it relates to the number of fixed points. So in very fortunate cases, we have that it coincides with the number of fixed points, but it tends to be at least a lower bound to the number of fixed points. So even when the Hadamard number is finite, you get some important information. Also, here, this result is for new manifolds. Doesn't really matter what new manifolds are, although if you want to know, this is a quotient of a nilpotent Lie group by a closed subgroup. But the important part for us here is that new manifolds are the manifolds having a nilpotent fundamental group. And for this reason, there is a lot of research on Hadamard numbers and classifying groups according to R infinity, but focused on nilpotent groups. I mean, there is a general quest on classifying groups according to R infinity, but there is a lot of work, a lot of effort put on nilpotent groups. And Yuri and I, we are very fond of solvable groups. So you see that most of our work is for soluble groups that aren't nilpotent, okay? And for those groups, so there are the solved manifolds, the manifolds that have solvable groups as fundamental groups. This does not hold in general. There are some cases where this is where we have some sort of results, but it's not so general as for new manifolds. But it's still useful in the group theoretical setup to know about the Hadamard numbers of such groups. So that's what I'm going to talk about now. So in group theory, having property R infinity or not having it might have implications on the group structure. And then to illustrate here, I'll show you one result in linear algebraic groups. If you don't know what those are, it doesn't matter, this is just motivation, but think of GLN, the general linear group. General linear group, so invertible matrices. So you take here, there is this result of Buni and Bose, which was heavily inspired in the work of Steinberg, that says that if B is a connected linear algebraic group defined over some algebraically closed field, we have the following. If you know that there is an automorphism phi of B that does not have infinitely many twisted conjugacy classes, then B is soluble. Of course, here we're taking algebraic automorphisms because it's an algebraic group, but you could just think that in this case, not having, well, algebraic R infinity says that the group is soluble, which is a completely group theoretical property of this group. So it's also interesting to know about Hadamard numbers in a group theoretical setup. And 2 years later, Buni and Bose, they showed a partial converse to this result. They showed that if B is soluble, then the Hadamard number is either 1 or infinite. And also moreover, if B is a Borel subgroup, if you're thinking about GLN, just think of the upper triangular matrices, then this group has R infinity necessarily. So all automorphisms have Hadamard number infinite. And then we could ask in an arithmetic setup the equivalent things. So we could ask, for instance, how does the Hadamard spectrum of some arithmetic group would affect its algebraic structure? So my collaborator is Yuri. Yuri is very fond of S-arithmetic groups, so we picked S-arithmetic groups. If you don't know what S-arithmetic groups are, I won't explain because they're they are not straightforward to explain what they are. But some examples of them would be SLNZ. So the special linear group SLNZ. You could take the special orthogonal group SO2N over, say, FPT, so the polynomials over the field with prime numbers. Or you can take GLN and then also over Z1 over M, so you can allow division by one integer in your group. So don't worry if you don't know. If you know about as arithmetic groups, that's great. If you don't, it won't be a problem here. So that's our main motivation and the questions we are trying to answer, but bear with me. So the first question would be, arithmetic groups, how the mass spectrum affect their structure? Also, if you take some S-arithmetic subgroup B, so Borel subgroup of a semi-simple group over a global field, then does this group have an infinity, as in the case of Boolean and Bose? And in case gamma does not have an infinity, it's also true that its Hadamard spectrum is contained in 1 and infinity, as in the previous case. So Yabara, he gave a partial answer to that question. He showed that if you take linear and finitely generated groups, then these groups admit some automorphism of finite order that does not, if this group admits such an automorphism of finite order, not having infinitely many twisted conjugacy classes, then G is virtually soluble. Of course, it's not a complete partial if you have that the group has R infinity, but it happens that only the groups are infinite order have finitely many, then you don't know if this is virtually soluble or not. Okay, so Yuri and I also contributed towards answering to those questions. So I'm going to explain to you what our main theorem is. Again, I'll be talking about, well, some very specific groups here. If you're not familiar with them, don't worry, because this theorem is mostly, it's a direct consequence of a more general but also technical result. And I'll be talking about the technical result, but I'll tell you precisely what the groups are. But in this context, what we've shown is if you take any positive integer n, that is at least 2, we can always find a global field, k and p. So here, p denotes the characteristic. It could be 0 or any prime number. So, okay, so for all n, we can find a global field np. And a family of finitely generated S-arithmetic subgroups, gamma and p, such that the Hadamard spectrum of gamma 2p is not 1 infinity, but if you take n to be at least 4, then these groups have R infinity. Now here I would like to stress out that we picked groups gamma that are non-nipotent soluble, and n here denotes the solubility class. So here we are saying that in the case of solubility 2, we have an example of a group that had a mass spectrum contains a number that is not 1 or infinity. But in case of higher solubility, we found groups that have a family of groups of arbitrarily large solubility class that have R infinity. Okay, but as I mentioned, this result is a consequence of a technical result that actually provides a way of checking whether a family of groups have R infinity. And as I promised, I'll explain what the precise groups are. So we just take groups that are groups of upper triangular matrices over some commutative unital ring. So just take the matrices that look like this. So here we plug some commutative unital ring R, and we are looking at the R points. So we are considering the groups of upper triangular matrices, but we are also considering some projective variant, if you want to know. So this is just the same group, but then we take the quotient with scalar matrices. So it's the same group, but subject to some relations in the main diagram. And then our main result, I'll be referring to it as our technical theorem of Yuri and I. It says that if you take an integral domain, and this integral domain has finitely generated groups of units, then if you want to know if, then to check R infinity for the previous groups I checked, you only have to look at you only need to check R infinity for the ring automorphisms of the integral domain. So when you take an automorphism, ring automorphism of R, this will induce two automorphisms that would be interesting for us. The same automorphism, but now seen as an automorphism of the additive group of R. That will be noted with alpha add. And then there is this that we call the flip automorphism. So this is tau alpha, just sends the pair RS to the pair alpha add S, alpha add R. So it sends to the image under alpha, but we flip the positions. And then our criterion is if we know that both alpha add and tau alpha have infinitely many twisted conjugacy classes for all ring automorphisms, then you get that all groups B and R and PB and R have R infinity. So in particular, you're taking all upper triangular matrices of R when n is at least 4. So this gives you a very easy way to determine whether matrix groups of arbitrarily large solubility class have R infinity. Instead of sketching a proof for this theorem, I'll actually give you some examples. The first one is when R is the ring FPT, so the polynomials over FP for some prime P. So let us show that, in fact, this maps alpha add and tau alpha have infinitely many classes for all ring automorphisms. So what do? We'll construct an element that has some interesting properties, and I'll explain why. So here we consider S to be an element of our ring that is given by the product of the image of the variable t under all ring automorphisms. This is an element of FP because, well, FPT has only finitely many ring automorphisms, so this is a finite product. And also, it's easy to see that S has to be a non-unit, because if S was a unit, because the identity is here, you would have T times something is S. And then, well, we can just multiply both sides by S minus 1. You get that T times something would be 1, contradicting the fact that T is a non-unit. So what do? We consider some proper ideals In that are generated by powers of this element S that we constructed. And we notice that this element S is a fixed point of any automorphism, just because if you take alpha of S, this is S. So alpha of S is just the product of alpha composed with all automorphisms. So this is equivalent to just taking the product of over all automorphisms. A bit of a noise here, sorry. So, oh my God. Sorry about that. There is some construction in the building. Okay, so we consider the this proper ideal because S is invariant by any automorphisms. We see that the ideal is also alpha invariant. And then when the ideal is alpha invariant, we are able to define ring automorphisms in the quotients of R by this In. So what we have here is R mod In. So the map would be alpha n sends this coset to the coset represented by alpha. And why am I constructing this idea? That's because there is this very standard result in this area that says that if you have a short exact sequence that looks like this, and n is invariant over the group automorphism, then this induces an automorphism in the quotient Q, here seen as G mod n, given by this operation, which is precisely the map alpha n that I just defined. And we have this very nice property that the Hadameister number of the induced automorphism is a lower bound for the Hadamard number of the original automorphism. So what happens here, precisely what we want, we have some alpha n's that are invariant. We have some ideals IM that are invariant by alpha. Then we induce this automorphism. And then by this lemma, we see that the Hadamard number of alpha at is bounded below by alpha n empty. Then I'm going to cheat a little bit because we don't have enough time. I'm not going to show this, but this sequence of alpha n is non-decreasing and unbounded. And this yields that we have that alpha at has infinitely many twisted conjugacy classes. Now, our main theorem says that anytime we have that every automorphism has alpha at, Hadamard number of alpha at is infinite, and the Hadamard number of tau alpha is infinite, then all those families of group are infinity. I'm not going to show this one, but we also show we can also show this one. So we conclude by the technical theorem that all the groups Bn, so all upper triangular matrices with coefficients in F and T, and also this projective variant have our infinity as long as n is at least 4. Okay, so I'm going to show a last result that will actually show a particular case of our main theorem. But for this, we need this lemma. This lemma says that if A is a finitely generated abelian group and phi is an automorphism of A, then having infinitely many twisted conjugacy classes is equivalent as to having infinitely many fixed points. So now we want to show the case where R is some ring of integers of some algebraic number field. So what we need to show here, following because of this lemma, we know that the underlying additive group is finitely generated. So we are so this is also abelian. So we are in this setup. So we know that automorphisms of groups of OK, they will, if I take group automorphisms of OK, they will have infinitely many twisted conjugacy classes, if and only if they have infinitely many fixed points. Now, using our previous theorem, we need to check whether alpha at and tau alpha have infinitely many fixed points. And then if we do this, the theorem will assure that all groups of upper triangular matrices over rings of integers for n at least 4, they have our infinity. And the same with the projective version. Now this is clear because Z is always contained in the ring of integers. And the ring automorphisms of some OKs, they fix Z. So for instance, in alpha, we see immediately that Z, the elements of Z, will give infinitely many fixed points of alpha. And then for the flip, we could take, for instance, the diagonal of Z, because then if you change the order, you still get the same element. So the fact that Z is contained in the set of fixed point of alpha already gives us that alpha at and tau alpha have infinitely many fixed points. Okay, so let's go back to the main theorem. This is just its statement. You don't have to read it again because I'm going to show just the case where we have characteristic 0. And then in characteristic 0, that's what it would look like. It says that if you have a positive integer 2, then there is a global field K and naught, and a family of finitely generated S-arithmetic groups gamma n, such that, well, in case of solubility degree 2, we do have some Hadamard number that's neither 1 or infinity. And if you take n at least 4, and then this at least 4 gives you a hint that we're going to use our main theorem, then those groups have R infinity. Okay, so what would be the answer here? We could take, for instance, K and naught to be just the rationals adjoining I, so the Gaussian rationals. Then its ring of integers just Gaussian integers. And we just take gamma to naught to be some semi-direct product of the upper unitriangular matrices. So here we are, those are 2 by 2 matrices with ones in the main diagonal, any element of Zi above the main diagonal and 0 below. And then gamma n naught is just the projective version of PBN Z. Here C3 is just the cyclic group of order 3, and then the semi-direct product is taken with the action given by J, this matrix. So, by our previous examples, we've shown that if we take gamma n naught, then PBN Zi has R infinity whenever n is at least 4. So this shows the second statement. And for the second statement, we have that there is a work of Caro and Peter that shows that, well, it's more general for crystallographic groups, but in particular, you have here that Z2 semi-direct product of C3 with J will have an alphomorphism, which is given by conjugation by this matrix, and it has finite Hadamard. But then because D and J, they commute, we can actually show that if you take that this map leaves this quotient C3 invariant. And then we know that here we have at least 3 conjugacy classes. And because of that lemma I gave you, the number of conjugacy classes of this quotient C3 will be a lower bound for the twisted, for the Hadamard class of the whole group, gamma to naught. So we see that because this one has at least 3 twisted conjugacy classes, we must have that phi d has precisely 3, sorry, then phi d has to have at least 3 twisted conjugacy classes, and then it's finite, so it's a number that is not 1 or infinity. Okay, so I'm sorry about the I don't know, nobody told me there would be constructions in the building, but yeah. So that's all I wanted to say. Well, thank you for your attention.